Hello and welcome to today's webcast brought to you by Laser Focus World and Endeavor Business Media. Today's event, Remote Human Body Temperature Measurement, will be presented by Prometeusz Jasinski, Applications Engineer, Infrared Detection at Recalibrate Technologies. My name is John Wallace and I will be your moderator today. Before we begin, a few words about the webcast technology. This platform allows you to customize your webcast to suit your preferences. You can move windows around by dragging on the title bar, or resize your windows by clicking on the lower right corner of any window. You'll notice a toolbar at the bottom of your console. These icons allow you to open and close the engagement tools on your screen. If you should experience difficulties with the audio or advancing of the slides, just press your F5 key to refresh your webcast console. There's also a help engagement tool if you need additional assistance correcting your issue. It's the yellow icon with a question mark. We encourage you to ask questions at any time using the purple Q&A icon on the toolbar. We'll address those questions in a Q&A session after the presentation. If we're unable to get to your questions during this webcast, we'll do our best to reach out to you afterwards. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the Laser Focus World website. I'd like to note also that a locked PDF copy of today's presentation is available. The PDF can be downloaded now or during the on-demand version of the webcast by clicking on the green Event Resources icon in the engagement toolbar. If you'd like to contact the Recalibrate team for any reason, you can click on the blue icon at the bottom that has an envelope on it. Now it gives me great pleasure to introduce our speaker, Prometeusz Jasinski.
Yes, so hello, Prometeusz Jasinski speaking here, Applications Engineer, as you heard. I have a couple of slides to share with you, so I would say let's get it on, and afterwards we can have a couple of questions answered, if there are any. Today's presentation is about animation, of course. Remote human body temperature measurement, which is a really hot topic in our days, as you may know. And might be also the reason why you're so interested in this presentation. But let's first have a look on why we should still care about this, despite some people saying it is mostly over and we don't have to take care of this too much. We can have a look into the history. Let's have a look 100 years ago. So there have been already some pandemics in the history, so why not learning from those ones? We had this H3N8 flu in 1889 till 1890, 1 million fatalities, so over 6% of the humanity died because of this flu. Then we had a very severe one, the Spanish H1N1 flu, 100 million people died, 5.5% of the population. It was only 28 years later after the first one. 38 years later, again, an Asian flu, H2N2, 2 million fatalities. Sounds more like the first one, still not much more because the population is growing, so 0.07%. Hong Kong flu was very broadly discussed in the media because it was already in 1968, 1969, so the people became more informed, and 1 million fatalities was quite severe with 0.03% death. Swine flu, not so bad 40 years later, but you can see that the severe ones were already quite some time ago. So the current disease, SARS-CoV-2 virus, has a fatality of 0.01% currently, so not really the biggest one, but we are still to go when looking at the recent pandemic. So one remark, the COVID-19 disease is not an influenza type virus, so some conclusions might be a little bit different. So the takeaways from this one are the new generation has forgotten about past major pandemics, so we're simply not used to how to deal with it and handle it. most presumably the pandemic will last more than 2 years. So after 1 year, still it is worth to look into solutions and how to support the people not getting caught by the flu so quickly. The increasing growth in population will result in numerous deaths. So we have quite a lot of people on the planet. So unfortunately, the total number will be really big. The increasing mobility of people will enable the virus to spread very quickly. So having something under control in one local spot does not mean that it will not become another hotspot in another place at the end. There will be likely another pandemic in the future. So everything what you invest now into systems developing something against pandemics most probably will be also needed in the future. So why can't we stop simply? It's a remark, we are actually the factories for the virus, so the body must handle the virus by itself, and we can only support the body once it was infected. The unfortunate thing is, fortunate for us, the virus needs to be, in order to be effective, must not kill the host. Yeah? So most of the people will eventually survive this virus. There is only a minority of people where the virus will kill those people. And looking at the humanity today, we must protect them as best as possible. And finally, only when about 60% of the people have been infected by the virus, the spread will mostly stop. So this is why you know maybe those curves which tell you how many active cases over time you have to expect. And the recent flus had the issue that every time when the flu spreads across the world, it is not the problem that just a minor portion of the people is getting very sick, but the total amount of people is very big. So eventually, after some time, without any countermeasures, the people which need some hospitalization will exceed our healthcare system. Yeah? So we need to gain some time into this one. So we need to flatten the curve, and with some time we have also the possibility to increase the healthcare capacity, so we can, we will have as many people as possible surviving this virus at the end. So how can we survive it with a low mortality rate? We need to increase the healthcare capacity, as you've seen, and we need to slow down the spread of the virus. So this we can do by increasing the physical distance between people and or reduce the spread of floating virus shells. So mask, disinfection, and so on. So this we are doing on a large scale already. And the second one is we need to reduce the mobility of those people who are actually then infected. So we need to identify those people as good as possible and then isolate them in order to reduce the spread speed of this virus. We will never be able to catch all of them. Typically, this is done at doors at gates, where you can have a look on one after the other person. And what you have to do then, when looking at those people going through gates, you need to go for those symptoms of the COVID-19 disease. And the symptoms, the top symptom is fever or chills. Yeah? However, those symptoms appear only 2 to 14 days after exposure to the virus. So again, you will not be able to find all those people carrying this virus with you. But the more, the better. So what is actually fever? It is not so clear when looking into literature. People generally regard fever everything about 37.5 degrees C above the body core temperature. But even a healthy person can have, depending on the circumstances it is in, for example, doing some sports or on a hot day and so on, the normal range can even exceed this. So we can have 37.5 and 38.5 for a perfectly healthy man. How can we measure the fever? The fever is actually measured mostly with 2 different approaches. 2 approaches on the head, where you can have a look into the ear canal, or on the forehead, or you can have the rectal measurement with a probe. Other regions you may consider to use, like arm wrists, or looking at some variables, some stuff which you are having around the neck or so on. I can tell you from experience, this has been done and tried many, many times, And those regions all over the place are poorly only correlating with the core body temperature. And what we're interested in is the core body temperature and not the surface temperature of the person. The requirements for a fever detection station, if you want to build one, would be, it starts always with high accuracy. You want to be as accurate as possible. And of course, the second question the customers ask us always is low cost. And this means also operation. So you don't want to have a sensor for a cheap price, but you need a regular calibration of the sensor. A fast, high throughput and high cleanness. This is the major reason why you cannot have contact type thermometers. And even the ear canal measurement is a contact type. So you need to stick this probe into the ear. So at the end, you're left for such a fever detection station only with a forehead temperature measurement. Then, of course, high reliability and stability are the requirements. Low power consumption, sometimes, especially when it's better operated, and then it comes with small size and portability being also sometimes a requirement, but not very often. And last but not least, in such a situation like we are now, the availability is actually a really big concern. You may be able to find a supplier on the market who gives you then sensors, you have samples, you build something up, at the end you try to order it, and it takes several weeks until you get the first sensor. So really at the first beginning, you should be sure that the supplier which you have chosen can deliver actually your demand. Measuring elevated skin temperatures. In the following, I'm simply assuming that you have a good correlation between the skin and body core temperature, because I'm talking only about the technical stuff, not about the medical stuff. So how can we make actually the temperature of the skin visible, like in this nice picture where you have from the forehead? And I would like to jump a little bit into the basics, because those basics are important to understand when building up such a system. And the basics are, you're looking at electromagnetic waves. The electromagnetic waves, which are emitted from the surface, have a wavelength. And having a look on the wavelength, you can see a nice plot here. I would like to take you through this one because it's a quite important one, despite it seems to be very crowded and difficult to understand. This wavelength, so the length of the maxima or minima of the electric or magnetic component, you can see on the x-axis. It's on the bottom. And you can see it's a logarithmic scale, so there is it's 1 micrometer, 1, 2, 3, 4, 5, up to 10 micrometer, and then it goes to 100 micrometers. Yeah. Below 1 micrometer, you can see that there is some rainbow-like structure. So this structure is the visible spectrum. Each electromagnetic wave in this with this wavelength is visible to the naked eye of the person. Everything to the right is infrared. So not visible to the eye, as well as when you go to the left, to the ultraviolet, and then to radiation. This is also not visible to the eye. When going to the right, with a long wavelength, the energy which is contained in this electromagnetic wave drops. So the bluer it becomes, the more energy you have in the system. So we're talking about waves which don't have much energy to penetrate through material. Then you can have a look on the probability to emit a photon with this wavelength. And this depends on the temperature of the surface. So you can see here different surface temperatures. It starts at minus 20 degrees, 0, 32 degrees C, so this would be around the body skin temperature, and then 100, 300, 1,000, and 6,000 degrees C. So you can see those curves start from the right and rise in the intensity and go to the left with a peak. And only when you are at 1,000 and above degrees C, then the eye starts to see some light. Yeah? But we need sensors which are actually sensitive to 10 micrometers, where you have the peak for the body skin temperature. So let's have a look what solutions we have. Important, the radiation, the total radiation. So when you integrate the whole curve along the wavelength, this is proportional to the temperature of the subject to the power of 4. So this will be needed to calculate at the end the temperature. So as I said, sensors must be sensitive to around 10 micrometers. And let's start with the task. We have the object on the left side, a sensor on the right side, and there is a distance between those. What sensor can we choose? On the left side, you can have photonic sensors. They simply count photons. Those are semiconductors counting photons. Eventually, they need, in most cases, cooling in order to be sensitive enough to those single photon countings, and they are very expensive. On the upside, they have a very high signal-to-noise property. I am talking about thermal sensors. Thermal sensors are called thermal because they get heated by photons, and you're not directly measuring those photons. They are much less expensive. They are also less sensitive, but on the plus side, they have a very wide wavelength range. So the photonic sensors are simply not established in high volume applications due to those reasons for the high price, for example. Then, when you go to thermal sensors, most of you know those nice pictures with the false colors. Those are generally created with microbolometers. Those microbolometers can be very compact and have a high resolution. And this high resolution is, for some systems, even a downside. The downside is that you need to actually digest all those pixels. So don't take into account what cost the sensor alone, but you need to take into account the whole system price. And typically they require a mechanical shutter for temperature measurement or a reference blackbody next to the object. So those are the two established methods to measure with a microbolometer and absolute temperature with a high accuracy. So because of this mechanical shutter requirements, I'm focusing on our solutions, which are, on the one hand, you can use pyroelectric sensors. They also have the downside that you need a mechanical shutter for temperature measurement, despite being very accurate and long-term stability possible. So what has established on the market in high volumes are thermopiles. They are by far most established for single pixel solutions. Thermopiles are using the thermoelectric effect, which means that you connect an N-type and a P-type semiconductor in a long chain. And when you have on the one side a ceramic and on the other side a ceramic connection, and you apply a voltage to those ones, you can have a heat difference. So this you know from those 12-volt coolers used in your cars. We are reversing this effect, which means that when you apply a temperature difference on the structure, you will get a voltage out. Technically, you can see on the right side already a picture of this one. This is a silicon structure, which is thinned with a membrane down to 1 micrometer. Sorry, there's written 1 millimeter, but it's 1 micrometer. This thinning is a MEMS process, which makes it a little bit more expensive than simple semiconductors. And on the around this, you have the silicon bulk, which is the heat sink for it one. You put in the middle an absorber, which is then absorbing the photons. It gets heated, and then you get at between the warm contact and the cold contact a temperature difference, which again generates a voltage. This voltage you can simply pick up with those two electrodes. So generally, you can assume that the voltage which comes out is proportional to the temperature difference between the membrane and the heat sink around it. So we need to know the temperature of the sensor's housing for reference, because it looks only for a temperature difference. This you will find in those detectors as an ambient temperature. So it's not just an additional feature which we are providing to tell you what is the sensor's temperature, but it is actually required to measure the temperature of the remote object. So for an analog one, it's a simple NTC. For a digital solution, we call it, or it's called a PTAT in our case. So back to the object temperature measurement and the sensor on the right side. The object, I assume, is opaque, which means that the infrared light is coming from the surface of this object. Yeah. So let's try to measure a spot on this object and not the entire object, because you have seen already at this picture that actually the forehead is not uniformly warm. So you want to have small spots measured at this forehead. This spot is emitting the photons in all directions. Yeah? But you can only measure a fraction of this radiation. So how do you do it? You are measuring only the surface radiation, I said already. When you put just a sensor in front of it without any optical system, then a simple aperture does not do the job, because the field of view of the sensor is collecting photons from a much wider area than the object itself. So first thing what you need to do is you need to have a look on a sensor which reduces the field of view down so that you are focusing only on this spot of interest. So the right choice of optics is important. So I give you an example. Here for a face scanner application, I show you a 4x4 pixel sensor. It's the TPIA 4.4 TL5.5. The L5.5 is the focal length of this lens, which is put in front. And with multiple pixels, you must use a lens in order to have a projection of the picture at the focal plane. This projection of the picture you can see here as an angle X and angle Y projection, and you can see the intensities which are picked up by the pixels, by the individual pixels, so the 4x4 pixels. Looking at this graph, you know that you have something like 30-degree field of view. So this is good enough for a face scanner in 10 to 20 centimeters distance in order to cover the full face and allow for movement of the face to the left, to the right, and keeping track of what you're measuring. When you come closer, then you can actually use even sensors without any optics. So it is not important that the field of view, like in this case, is a very big one, because with a short distance of 0 to 0.5 centimeters, then you have no problems with the optics at all. The radiation, as I said, is the temperature to the power of 4. So the thermopile voltage is proportional to the total energy which is being seen by the sensor. And this is proportional to the temperature to the power of 4 of the sensor. But you must not forget that the sensor has also a temperature, which means that it is not only receiving photons and heating up by those, but the temperature which is growing then, of course, leads to an emission of photons on the other side. So this is the ambient temperature compensation, what we're talking about, which is necessary for thermal sensors. And here you can see this compensation is written into the formula as a minus T to the power of 4 of the sensor. So the sensor temperature, again, needed to be understood. One remark on emissivity, because you will see in those detectors that you have a parameter which is called emissivity, which you can adjust. For skin, it is not so important because the skin emissivity is around 96%. What does it mean? When you look at this picture of this left cube on the right side, this is actually an aluminum cube which is at an elevated temperature. The temperature is around 50 degrees C, and you try to look with a microbolometer what the temperature of this cube is. This cube has, like you can see on the lower left and lower right, has a black and a white painting on one side, and then it has two other sides where on the left, the lower left, you can see it is reflecting, so really like a mirror, and on the right, it is more frosted. And then you can have a look into the infrared spectrum, and actually you will notice on the one hand that what you can see with your bare eye, so having a black paint or a white paint, does not mean that it is a black or white body in the infrared spectrum, because both surfaces give you the correct temperature reading. So what appears to be colorful for your eye does not mean that it is also the same for the infrared spectrum. Also, you can see that actually for the shiny surfaces as well as for the frosted one, the cube appears to be cold, despite it is not. So if you want to measure an object temperature where the emissivity is not close to 100%, then you might be in troubles if you have a very shiny object. Yeah? If it is something in between, then of course you need to adjust the emissivity so you know how much is reflected in the cube. So let's come back to our setup where you have the object on the left side and on the right side the sensor. And the formula, which you need to use, has now this emissivity inside. So you have the emissivity of the object to the power of 4, minus the temperature sensor to the power of 4, and then you have to add the radiation which comes from the ambient, which is being reflected from the object into your sensor. So this is the 1 minus the emissivity to the power times the temperature of the ambient to the power of 4. Now you can see the formula has actually the total energy, the temperature of the sensor, and the ambient, which you need to determine in order to tell what the object temperature is. So as I said, skin emissivity is 96%, and now comes a very important assumption. This is in most cases really not well understood from engineers when using thermal sensors, that the ambient temperature is assumed to be the same like the sensor temperature. So when you have a system which is heavily heating the sensor, be it a microcontroller which is doing a lot of processing, or when the sensor is being heated by sun but you're looking in a cold spot or a cold space or so, then this assumption is not true anymore. So you must make sure that the ambient temperature and the sensor temperature are actually the same, because only then you can have a simplified formula of this one, where you say that with the ambient temperature being the temperature of the sensor, the object can be determined by the voltage of the thermopile divided by the sensitivity of the thermopile times the emissivity plus, so the ambient temperature compensation to the power of 4, and then you take the fourth root out of this one. So C is a calibration factor, which is highly setup specific, which means if we provide you a sensor, it is for a certain setup pre-calibrated. Yeah. If you change this setup, meaning changing the distance, changing the object, changing the emissivity, whatsoever you're changing in your setup, your reading will be different from what you get from the factory. This is why you have the possibility to change the emissivity of the object. And changing the emissivity, you can see, is actually the same in the formula like the component sensitivity. So by changing the emissivity, you can in addition compensate for a change of your setup. Yeah? So once you put the sensor in front of the object and the reading is not correct, when the object is warmer than the sensor, then you can change the emissivity and have a look what the correct reading would be. One remark, when the object is at the same temperature like the sensor, the net radiation is 0. So this voltage of the thermopile is also 0, which means you can change in the emissivity as much as you want. You will not see any effect because the ambient temperature is the only factor which goes into the object temperature. Yeah, maybe one remark on thermal shock, because I said the ambient temperature must be same like the object temperature. When you put such a sensor into the ear canal, you will notice that you have at the very beginning a very different reading from what you have expected. This is shown here very badly, you can see it, but there is a scale over the time of the error of the signal. This is actually from a test setup, so this is not real data, but this is a standardized test setup to actually see how well such a thermal shock is being compensated by a sensor. And we are applying high-tech materials, which is mostly copper, very high-tech, but we have patented this setup, which means that with copper you have a very quick thermal flow from the hotspot down to the base plate, and then we call it isothermal packages. You will notice it that there is written TPIS and TPID. So this I identifies the isothermal package, which in turn will give you a much better thermal shock compensation, which means such an application where you have quick changes of the ambient temperature and the sensor temperature, isothermal plays a big role. So another remark on medical grade sensors. You will find on the market sensors where you can buy them with medical grade accuracy. This is nice to have, of course, really nice to have such a sensor, but then you put it into your setup and eventually you are responsible for your device to be accurate, which means our customers must be able to prove with their setup that the stated accuracy of the final device is reached. We are not in charge for this. Our customers must ensure that the whole setup is accurate within 0.3 degrees C, not the sensor alone, and this within this 10 to 40 degrees C ambient temperature range. So we at Excelitas, being the first on the market, and we really can say that we are the market leader for such sensors, we simply are sure that we must not offer medical grade calibrated sensors because the customers are being fooled by this one. When you put it into a package, you will change the setup, and then the calibration doesn't work anymore. But we can guide you to medical grade accuracy, which means we can support you setting up your calibration system on your side. Which means it turns, I'm encouraging you, if you want to have a medical grade sensor, to work with us, then having the calibration set up in the factory. Then you put such a sensor in this particular application of a face scanner. Let's say like this, you don't have a fixed distance between the sensor and the object, because the object is your head and you cannot still completely stand completely still, which means you're changing the distance between the sensor and the object. Of course, there is one thing which is changing, which is the coverage of 1 pixel in respect to the hot surface which you're looking at. The closer you get, then the smaller the coverage of at the object is. So this changes already slightly the temperature reading. But there is another contribution, and this contribution is called stray light. So this is indirect infrared radiation, which comes from very large angles into the sensor package, is being reflected inside the package onto the chip. And changing this stray light component changes then, of course, the temperature reading. Fortunately, there is a countermeasure for this one. You will find it sometimes on the market already pre-fit. We can show you how to set something up. This would be on the right side a simple lens hut. This lens hut is already known from photography. When you have a camera, the camera is usually used with a lens hut in order to reduce the stray light component. So if you want to have such a stray light reduction, then use please a highly thermal conductive material made from aluminum or copper. This is important to have thermal uniformity along this whole setup, because you remember, we are assuming that we know what radiation comes in, and the radiation must be either at sensor temperature or at the temperature of the object. Everything in between, it is very difficult to calibrate. Then use a high emissivity coating, black, to reduce the reflections, because when you leave it shiny, as you might think, to reduce the effect of self-emission of photons, then you are left with stray lights again, because this reflects into the sensor indirectly. You can also apply the trick from photography, simply putting grooves to reduce the reflectivity even further. But please do not cut into the sensor's field of view. So you've seen the field of view diagrams. Look at those field of view diagrams and have the opening angle of this lens hut then fit to this one. And finally, once you change again the setup, this is change of the measurement setup, you need to recalibrate the sensor with the hut. So you need to adjust the emissivity of your sensor to get the correct reading. I can actually show you what it means and how much it differs with and without the lens hut. Here on the, you can see is a measurement over time of a sensor looking at the black body, a flat black body with a 50 times 50 centimeter surface. You go from 25 centimeters to 12 centimeters, and you can see that the temperature changes by almost 1 degree C. Yeah? Applying this lens hut reduces this effect to down something like 0.1, 0.2 degrees C. So really tremendous improvement with the lens hut. If you use a single pixel sensor, there is also the possibility to use an internal reflecting mirror. This is called the IRA type. So TPIS 1T1256 IRA tells you that there is an internal reflector fit into the package, and with this one you have also a reduced stray light. This is a simulation which shows you how the cone is then mostly looking into the front. This would be a field of view which you can achieve, and when you look at this graph you can see that the field of view with such a device is slightly more than 10 degrees. This is of course more than you can achieve with the lens. This is why for most applications our customers choose a lens type sensor, because the field of view is simply smaller. Then other influences, stray light, I said stray light and field of view coverage are the main reasons for distance dependency of a temperature reading. Now, I talked about this a lot. Then you have, in the application, customers are coming back and asking us, can we put actually a window in front of the sensor because we want to protect the sensor? I can tell you, such a sensor does not have to be protected. The surface of silicon is actually very robust, and even when you have sensors with just a flat window with an anti-reflective coating, even those ones can withstand cleaning processes without any problems. But despite this one, still you might ask, can we have the appearance of this whole device nicer by covering the sensor with something? And this something must be high density polyethylene, silicon or germanium. So those are the three most commonly used materials. This is possible actually to put in front of the sensor. High density polyethylene is for high accuracy measurement very, very difficult because high density polyethylene absorbs at 400 micrometers thickness already 50% of the radiation, which in turn means that 50% of the radiation which the sensor sees comes actually from the temperature of this polyethylene. So again, when you fit something with a transparent material in front of the sensor, if you must do it, please try to make the whole setup isothermal, so that which means that this transparent material as well as the sensor are at the same temperature like the ambient. Any material, this is why I say any material in the field of view affects the net radiation and significantly reduces the accuracy. Any object with a temperature above 0 Kelvin, directly or indirectly visible to the sensor, should be at the same temperature as the sensor or the object, which means even when you have a package, and when you have, as I said, also the lens hut, which might be not directly visible to the sensor, through stray light, it is still visible to the sensor, and we're talking about accuracies down to 0.1, 0.2 degrees C, which you would like to achieve. And this is only possible when you have everything at the same temperature. I'm saying at the same temperature over and over, but this is really a pitfall which is commonly made. Then, what about the filters which we are using? You can have a look on the transmittance for plain silicon, which is the case for standard uncoated lenses. This transmission goes down to below 1 micrometer, which means when you have in your application another source of radiation like an LED, a laser, whatsoever around 1 micrometer, this can actually disturb your sensor. In such application, this is in most cases not the case for a fever scanner, but if you have something like this in your application and you don't want to see it, then you might think about sensors using coated lenses or flat windows with a coating. So our flat windows with a coating you can have here is a standard one with a cut-on starting from 5.5 micrometers, so you are not affected by the white light and lasers. And also I would like to mention long-range temperature measurement and high humidity measurement. In such a case, you may use a so-called G9 filter. So this G9 filter has a small transparency window between 8 and 40 micrometers. And if you look up what the absorption of water vapor in air is, this window fits nicely into the window in the air. So you have less distance dependency for long-range measurement. This is typically used for those pyrometers, so handheld pyrometers which have to measure over several meters distance. Yeah. But again, I'm coming back to the application of a fever scanner. Typically, you will have to get close to the person. So please don't believe that you can measure over several meters a very high accurate with a very high accuracy a person. It will be very, very difficult to achieve. So this is why our proposal for a phase scanner, which you can produce in big quantities, would be something like this one, where you take simply a 4x4 thermopile sensor, which is factory pre-calibrated. However, If you want to have medical accuracy written on your final device, then you need to recalibrate it. Yeah, so we can help you to achieve an 0.3 degree C laboratory accuracy, and I'm writing laboratory accuracy, because in the laboratory you will have this 0.3 degree C. Yeah, and this is also a common misleading of people on the market. Sometimes I see fever detection stations being as accurate as 0.1 degree C. I can tell you from experience, this is only laboratory conditions, and when you put it into the field, there is no way to have this accuracy in the field. Yeah. Then you can combine it with a webcam for this one, like this one, and the webcam is actually used to constrain the distance and to control the coverage of the sensor. So you need to guide the phase into the position. We do it simply by showing an overlay over the measurement spots, and then provide some software to determine the results of previous measurements. And based on those measurements, you can provide the feedback of abnormal readings. So you get rid of this problem that actually you require to have laboratory accuracy in the application by simply comparing the measurements from one person to the other. So you measure 10 people, after 10 people you know this is your reading, and if the 11th people is sticking out of those 10 people, then you can say, oh, you should redo a measurement with a higher accuracy device. So a real accuracy in the application, a medical grade device, which actually needs a close proximity. So I haven't seen on the market now medical grade devices which are measuring with a medical grade in several meters distance. Yeah? So it's always ear or forehead thermometer. So finally, what you can achieve and expect from such a sensor, I would say, is in the application something like 1 to 1.5 degrees C. Also seeing some effects from the surroundings, from a non-uniform heat up of the sensor, and so on. So real application accuracy, which you have to achieve, which you can achieve. Yes, so I hope your ears are not bleeding yet, and we are at the end of the presentation. So are there any questions which I might answer?
Thank you, Prometeusz, for the presentation. So yes, we're now in the Q&A portion of the webcast. So once again, to ask a question, use the purple Q&A icon on the toolbar. So first question. Can thermopile temperature sensors exist in multi-element arrays similar to microbolometers?
Yes, they can. However, a thermopile needs to achieve the highest signal-to-noise performance, needs a significantly larger surface, which comes with the larger system size. So thermopiles in such a configuration have, on the one hand, the nice benefit of having a large field of view because you have a big chip size. But for this particular application, it then requires a long focal length to reduce the field of view. So there is always a trade-off between the amount of silicon which you need to set up something like this and the price which you want to pay at the end. So I would say that devices above 32 pixels times 32 are simply too small in the pixel size to have a good signal-to-noise performance. This is also a good question in terms of signal-to-noise performance. Also, don't be fooled on those numbers because all those sensors can achieve 0.1 degree C accuracy and precision. Precision means from frame to frame measurement, because all those devices on the market provide a filtering. Of course, the more you average, the less noise you have. Yes? But you are interested rather for such an application where you put a head in front of the sensor as a quick feedback. So the time constant of the system has to be low, which means, again, in turn, you would like to have rather less pixels, but big pixels to have a good signal-to-noise performance.
Okay, next question. What is the accuracy of the ear thermometer?
The ear thermometer must be better than 0.3 degrees C in laboratory conditions. What in the application comes out in accuracy is the medical correlation between the ear and the body core temperature, and this is of course worse. So when you compare it to rectal measurement and the ear and those two readings, you can be easily off by 0.5 degrees C.
How can the temperature of the object be measured if the ambient temperature is higher, such as 40 degrees C, than the object, such as human body temperature at 36.5 degrees C, from a distance of 1 meter?
Yes, so then we come again to the ambient temperature compensation. Maybe I can look up the formula. Let's jump to the formula. Give me a second. It should be something like this one. Yes. So let's take the next one. You can see that this voltage depends, as I said, on the temperature difference between the or the net radiation which you have. Yeah? So in a case where the object is colder than the sensor, actually you are measuring a negative voltage because the sensor is cooling down. The inner structure, the membrane, will be colder than the sensor's bulk temperature. So you get here a negative one, and then the ambient temperature compensation takes again the value to the right reading.
Okay. Next, what is the furthest distance for a top-of-the-head temperature measurement from a ceiling-based sensor?
For a ceiling-based sensor, you will be not able to measure the forehead. Yeah? What you need to do is to do it with a direct sight on the forehead. There are actually two measurement spots which I am aware of that correlate nicely with the body core temperature. When you look up the market, let's put up this picture, and those are just in between those two eyes. It's not actually the warmest spot, yeah. So between the eyes, there is a spot which correlates nicely with the body core temperature, and you can see also in this picture here the sides. Yeah, there are some veins running just below the skin, and those sides are also nicely correlating. But actually, you can see those sides might be not very very good for such a remote temperature measurement because you need to put the hair aside. So if you have long hair, you will not see those sides. And when you put the hair to the side, then the skin is actually still too warm. So you need some time until it cools down and adjusts so that the reading is then correct with what you have previously calculated. Because, as I said, the skin temperature is still not the body core temperature. What you will see at the skin, let's say it's 34 degrees C, you need then to correct for this difference of 2.5 degree or more or less with the body core temperature. So the question was, can you measure it from the top? No, you cannot measure it. You need to measure it from the front, from the side. And then if you want to have a long distance measurement, then of course, the longer the distance, the smaller the pixels must become. So we need more pixels to actually measure this one. I've seen devices on the market which are nicely performing in such a case with a very high pixel resolution. However, please have a look and notice that they are always comparing the measurement to a reference black body in this distance of the person. So when the person is not at the same distance like the reference black body, then you might be very strongly affected by not only distance dependence, but also other effects like absorption in the air.
Mm-hmm.
So yeah, maybe to answer this one, yeah, sorry, maybe I didn't answer yet the question. So I don't believe, maybe just a general comment, I don't believe that it makes sense to measure above 50 centimeters to have an accurate measurement. Yeah. And the accuracy will still not achieve medical grade accuracy.
Well, that has relevance to this next question. Is there any solution that can be implemented to create an FDA-approved fever screening at 1 meter?
I am not aware of this one, but I might be wrong. So I'm very open if you provide me a solution doing this. Everything what I know is you identify those people who are sticking out of the crowd or are warmer than a black body, and those people you need to take out and then remeasure actually with a high accuracy device by penetrating the ear canal, for example.
Mm-hmm. Why do the temperature readings decrease as we move away from the sensors? Even smaller field of view sensors also have decreased with the distance.
This is, once again, the distance dependence through stray light, because the further you go away, the more you see actually going from the sides of the object, which are also partially reflected from the inside of the sensor. So this distance dependence you can greatly reduce by having a long tube with, actually, when you look into those devices, I have shown a picture of this one, this pyrometers have a quite low distance dependence starting from several meters away. The biggest distance dependence you have from 0 to, let's say, 50 centimeters, and then it decreases less. And those devices are so long just because there is a very long tube inside reducing the stray light, and the sensor is just sitting at the very end, just behind this display. Those are the pyrometers. So this would be such a device which shows you a quite low distance dependence.
Can the single pixel sensor be suitable for measurement of temperature at distances of 1 meter?
Only for comparative measurements. Yeah, so you can say this person is warmer than the other person. The problem with 1 pixel is actually that typically the field of view is too large for 1 meter. Yeah. Also, with the 4x4 solution on our side, the pixel size becomes very big since we have the same focal length and similar pixel sizes. So you would need what you would need then. You would need even a longer focal length, which elongates the whole package of the device, and then you get into troubles again with the thermal uniformity at the sensor. So it is simply not recommended measuring in a very long distance.
Mm-hmm. Okay, this is a follow-up question to an earlier question that you answered. At a distance of 1 meter, the view of the sensor includes a large background around the face of the person. If the temperature of the ambient is higher, can the sensor still detect the temperature of the face? Perhaps the issue is for the software to identify the hottest point, which may be the ambient and not the face?
Yes. So this is why in this example, we have shown that you might use, for example, a camera with a face detection software, which you can have easily in any software package. Another possibility would be to have a proximity sensor. Proximity sensor, an active proximity sensor with a low field of view, which will simply tell you that a person is in the right spot.
Mm-hmm. Next question. Does ambient always affect the temperature measurement? And is it the ambient from outside, from outside, well, let's see, ambient from outside from object, or from around the sensor if the sensor is inside a box or casing?
Long answer short, yes, it affects, but due to many reasons. And the biggest reason I see actually, let's do it really from the application side. It's the body itself. Yeah? I, for example, did for myself a test. Set up such a sensor and with a very accurate reading, an FDA-approved device. Just go for a walk in a cold winter, let's say 10 degrees C outside. This is Germany cold. You go outside, be just 5 minutes outside, come inside, and you have easily 1.5 degrees C less on the surface of your skin. Yeah? So there is from the application side, from the skin, an error which is can be very tremendous when you have strong differences in temperatures, the ambient temperatures, and also, as I said, when you have very cold surroundings and you have a strong heat source. Be it a microcontroller, a display, or whatsoever, which is heating the sensor from one side, then you get a temperature gradient inside the sensor, and this is also affecting the sensor. So cold temperatures are generally the difficult condition for an accurate measurement, not the warm conditions.
Mm-hmm. We have time for just a few more questions. How does the skin temperature translate into the body core temperature?
Yeah, so this is then, of course, a question which everybody is asking us. We are supplying the market, most of the market for those sensors, for those sensors, or with our sensors. So we have quite strong insight into those details. And however, this puts us unfortunately into the position that we must not disclose too much of this information. So getting a sensor from us means that you get a device where we support you in the measurement of a surface which is controlled in terms of a black body. When you want to know the correlation, so the FDA approval, the correlation between the skin temperature and the body core temperature, you must unfortunately get either the data or the correlation data from somewhere else or perform your own studies.
Next question, wouldn't more pixels help to increase the accuracy?
Yes, so the more pixels you have, the smaller the measurement spots are. Yeah? So indeed, I would be also in favor of having more pixels and smaller pixels. However, as I said, the smaller the pixels, the less signal-to-noise performance typically you have, and the system cost increases. Yeah? So we are operating at the sweet spot where you can produce devices which you can actually supply to the market below, let's say, $100. Yeah, and this is our target for the market. So high volume applications which are just good enough to help you identifying those people, and then you have to remeasure.
Okay, and the last question, and this has relevance to what you just said, what price are we talking about for such a sensor?
Yes, of course, everybody is asking this one. So this is a nice question. You might have a look on DigiKey or whatsoever. What are the prices divided by 10? You'll get a feeling for this one. However, I can tell you from experience, just talk to our team and get a quote, and be realistic with your quotes. Talk to us, and I'm pretty sure you will be not surprised, nobody surprised by the prices. I, as applications engineer, I cannot tell you too much about this one. Sorry.
Okay, and my own last question to you is: do you have any closing remarks?
I would say, just talk to us. Yeah. So our motto is engineer to engineer. As you heard me here, you can reach out via mail, you can have a phone call with me and our team. So our strong support will guide you to a solution, or especially at the beginning of the system definition, when you're doing your feasibility studies, please just ask us and come with ideas to us, and we will tell you, yes, we think this is a good thing, you should go on, or maybe try it differently and you might have success. So don't lose too much time by doing your own research.
I'd also like to remind the audience that if you would like to contact the Excelitas team, there's in the remaining few minutes, there's a blue icon at the bottom with an envelope on it. Just click it and you can email them. So now I'd like to thank today's speaker, Prometeusz Jasinski of Excelitas Technologies, for today's presentation, Remote Human Body Temperature Measurement, which is, of course, quite relevant. And I thought that Prometeusz did a very thorough job of covering the design of these devices. I'd also like to remind you that the webcast on-demand version will be available on the Laser Focus World website, and the link to the archived webcast will be sent to you via email within the next 24 hours. On behalf of Laser Focus World and Endeavor Business Media, we thank you for joining us today and look forward to serving you with future webcasts.